Morning, everyone. Thank you for coming on a Saturday morning. I appreciate it. So I have to make it worth your while, so I will tell you many stories and many secrets during my talk today to help give you perspective. I think the way I like to begin is to just think about, well, let me make one comment. I put this subtitle on this cover slide about this article, which was just published last week, by the way. It's a pretty long article. It's about 25 pages. I recommend, if you're interested in following up on what I talk about today, that you read this. It goes into a lot of the detail in terms of the theory behind what we're doing, and also it talks about practical steps as well. So, useful reference. But let's talk about the past a little bit. So, I would say from the beginning of the work with the DNA Storage Alliance through yesterday, there's not been a day involving a presentation from someone from this community where they haven't talked about the motivation for DNA storage predicated on this concept of this growing volume of data, so zettabytes of data. So therefore, we must do DNA storage. The question is, what's the motivation for doing compute with DNA, right? So let's talk about this a little bit. It'll set the stage for everything else that we'll talk about later on today. And I'll advise you at the beginning that this will be a very market-centric kind of presentation. I'll give you a perspective about what's going on in the market, how that gets reflected in technology, and how one, from my opinion, should go about attacking opportunities in the market related to DNA. So we begin with a quote from 2006, to outcompete, one must outcompute. This has become mantra in the hallways of Washington, D.C. The Council on Competitiveness is sort of a lobbying group on a variety of technology fronts and so on, but they have a thread in their organization that focuses on advanced computing. And the importance of the message is that it relates computing with business, with competition, and all that that implies. That is, don't pursue computing just for the sake of computing. Do it with a purpose in mind, and that purpose, from the U.S. perspective, is to compete economically and in other ways as well. So why do we compute, right? Why do we get concerned about zettabytes? Why do we compute? Two sides of the same coin. The motivation for computing is to gain strategic insight. Well, what do we mean by insight? It means an understanding of some phenomenon, some process, something in a deeper level of knowledge than we had previously. Insight that can be leveraged into some sort of commercial advantage or other sort of competitive framework. So I'll give you an example. And by the way, the systems on the right are some of the systems I did at IBM. Closest to the text is a blue gene architecture. I think that might be from Argonne National Lab. Lower right-hand corner is the Barcelona Supercomputer Center, which I started with Matteo Valero. And on top is the last system I did at IBM before I left, which is a Summit system at Oak Ridge National Laboratory, and was the Department of Energy's major step towards getting exascale computing. And these systems are bigger than the ones that preceded them. And the systems that these institutions have now are bigger than these systems. And it's all in this pursuit of gaining strategic insight. So I'll tell you a little story. Back in roughly 2004, 2005, when we introduced the blue gene architecture, which is a highly massively parallel system, one of the first customers was Argonne National Lab. They went from a small cluster computing infrastructure to a blue gene system, which took them to 64,000-way parallelism. Now that number may seem quaint in today's terminology, but back in that time, this is a big deal. They immediately applied an application to the new platform that was dealing with theories that they had developed in material science, and it revolved around the ability to model the interaction of molecules of this particular material. And after a little bit of time, they called me up and they said, we have to change our theory. And I said, why do you have to change your theory? And they said, because when we scaled the application to 64,000 way from 256 way, we discovered insights that we didn't anticipate previously. So they used computing as a way to inform themselves that reflected itself in a redefinition of the material science theory that they had been propagating, and they thought, by the way, was settled science and settled theory for quite some time. So it's just an example of how one can derive insight, but it also explains why people are motivated to get bigger and bigger systems. By doing that, by bringing more compute power to play on a problem at hand, it presents them opportunities to really get some sort of advantage. So new actions, behaviors, new insights, new theories, all these things come from it. And this is not just national labs and research centers. If you look at oil companies, finance companies, obviously other university research domains and so on, there is a consistent pattern of interest in getting more and more compute power to be applied to problems at hand. Many of you have probably experienced this. You use it in your daily work. Some of you may even have used my systems, for which I thank you. But there's more to this than just getting more insight. And by the way, whenever one of these systems is purchased and deployed, there's big press announcement, ribbon cutting, everybody is happy. The Summit system on the upper right-hand corner, Oak Ridge paid me $250 million for that system. So it was a big deal. And that's the way it goes. But we should talk about behavior at the parochial level, at the individual researcher level, because no matter how big these systems are built, they're a shared resource. So at Oak Ridge, for example, working on the Summit system, I don't remember now, it was maybe 250 petaflop systems, something like that, something in that neighborhood. That was meant to serve a community of 3,000 computational scientists. Here's a question. How many of those scientists you think ever got to use that system entirely for their own project? And if you say 0, you're on target, right? So that's why we have job scheduling software in the computing industry. And by the way, you can say, well, these are supercomputers, there are other computing architectures. This stands as a proxy for cloud computing as well. The point is, physical computing resources are limited always in all circumstances, and they're shared, and the sharing creates opportunity for people like us. Because if you're sharing a resource, it means that not everybody has what they need when they need it or all the time. So if I'm sitting in Oak Ridge and I have this grand ambition to do an investigation on a material science theory, and would really love to get my hand on 2 million processing cores, and they tell me I can have 10,000, probably not the happiest person in the world. Now I'll take it, it's better than 0, but you really, really would like to get the full access to that compute power. So intrinsically, computing, whether it's manifested in the cloud or manifested in big systems like this, are a shared resource, and it implies that you rarely have what you want, and you make do with what you get, okay? All right, so I'm also cognizant of the following thing. This is a very mixed community that exists in this auditorium today, people with wildly diverse backgrounds. So my next slide is going to be about definitions that'll hopefully help us through the rest of the presentation. So I want to give you a perspective about more on this issue of why compute, why it should be of interest, and why it has an appeal to us working in the DNA community. And we'll start with a couple of definitions on the left-hand side. Everything we're going to talk about today with respect to computing is going to be based on parallelism, right? And it's going to be parallelism because that is the intrinsic value of working with a molecule like DNA in a computational sense. You can do things in parallel. We'll get into technical details a little bit later on based on some of the experimental work and other work reflected in that paper. But parallelism is the key as we go forward in our discussion today. Well, parallelism can be defined in a lot of different ways. I've chose to do it in terms of scaling here. These are simple definitions. You can Google these and come up with your own versions of it. We have strong scaling, which basically says that if I have a fixed problem of fixed size, and I apply more computing resource to it, I can reduce the amount of time to solution. makes sense. I double the number of processors, voila, I suddenly have a solution half the time that I had previously.